Welcome back, AP Chemistry students, to Unit 1, Atomic Structure and Periodicity. Today we will be talking about Unit 1.3, Atomic Structure. We started this day out by doing the second part of our copper chloride lab. If you were in class, you did that. If you were not in class, then your partner probably did it for you. In 8th grade, you learned about the parts of an atom. Atoms have three fundamental parts that we will focus on in this class: protons, electrons, and neutrons. Protons are the positive part of the nucleus of the atom, the center of the atom, and they provide the atom with a lot of its characteristics. It is the protons that determine what an atom is. If you have one proton, you're hydrogen. If you have two protons, you're helium. We symbolize protons with a P with a superscript of plus. It's a shorthand for protons. Protons have a definitive mass in grams, but that mass is infinitesimally small. So instead, we say a proton's mass is just one unit of mass on this scale, or one atomic mass unit. Protons have a positive charge, and that's actually a voltage, but again, this is such a infinitesimally small value that we simply say protons have a +1 charge. For every proton you have, that's one more positive charge within the nucleus. Now, since protons have a charge, you know from just playing with magnets as a child that similar charges will repel one another. So two protons next to one another would have an extremely high amount of energy. So to separate them from one another, we have neutrons, which have no charge. Neutrons have a mass that is almost the same as protons, so we'll again say that they have a mass of one atomic mass unit, and they have no charge, and theoretically the function of neutrons is to separate protons so that they are not next to one another, they don't rip the atom apart. Electrons balance out the charge of protons. While protons are positive, electrons are negative. However, electrons repel one another, and atoms have multiple electrons, and so they are not in the nucleus. They spread out at different energy levels around the nucleus. Different amounts of energy cause them to go further and further out the more energy they have. Electrons are one fraction of a proton, and so while they do have a mass, that mass is so small it is negligible. And so we say that electrons have no mass to them. So this is the general model of an atom, with a dense nucleus where almost all the mass of an atom comes from, in a large area where electrons could be the electron cloud or electron energy levels, which makes up most of the volume of an atom. So an atom's nucleus is extremely dense, lots of mass in a very small volume, while those energy levels are mostly empty space. So the fact that two things with similar charges repel one another is known as Coulomb's law, and really Coulomb's law focuses on attraction. Two objects will attract one another when they have opposing charges. So something positive will attract to something negative. And the bigger that charge is, the bigger that attraction. Now, those charges are given the variable Q, so this force of attraction between a +2 and a -2, a 4, would be much stronger than, say, a +1 and a -1, where your force of attraction would be just 1. The charges are just half the equation there, because Coulomb's law also states that the greater the distance between two objects, the weaker the attraction. So I sometimes refer to this as the law of long-distance relationships, because long-distance relationships don't work. The further you are from the person you are dating, the less likely that is to pan out. So in Coulomb's law, that distance is represented as the denominator, because the greater this distance is, the smaller the force of attraction will become. We can use Coulomb's law to explain all sorts of things. In fact, Coulomb's law and thinking through Coulomb's law will give us a good idea about atomic structure, how atoms set up this particular shape or design. So it just requires you to think a little bit. In these two pictures, A and B, I've got two different scenarios. Both electrons are the same distance from their positive counterparts, but which one is stronger? Which one has a stronger attraction? B must be stronger because here we have two protons. That is going to have a much stronger attraction pulling that electron in than, say, having just one proton. So this electron will be pulled with greater force than in example A. All right, here's A again, but here's another scenario. In C, the distance between our proton and our electrons are different. So in comparing the force of attraction between A and C, A must be a stronger attraction. This electron is going to have a much greater attraction for this proton than this electron. And lastly, example D shows a scenario where we have 3 protons and 3 electrons. If we were going to try to remove one of these electrons, which one would be easiest to take away? Now, when you remove an electron, it's known as being ionized. So if we're going to ionize this atom, which one would be easiest to remove? The one all the way out here would probably be easiest to remove because it's not as close. So this attraction is much stronger than this one, but also these electrons that are near the nucleus are going to repel the electron out here, weakening this attraction even more. So if you had to remove an electron, if you had to ionize this atom, the one on the outside would be very easy to remove. So comparing them, if we were going to ionize all 3 of the atoms of the examples we've looked at, which one would be the easiest, which one would be the hardest? All right, so let's work backwards. The hardest electron to remove would be the one with the greatest attraction for the nucleus. And while this has 3 protons, this electron down here is strongly attracted to this 1 proton, and there's nothing getting in the way. So we would probably say that this would be the hardest atom to ionize, to remove that electron from. Which brings us to A and C. Which atom would be hardest to remove an electron from, or which atom would be easier? Well, A and C both have the same distance to the electron that's furthest from the nucleus. However, A also has that repulsive force, meaning this electron is fighting both the distance and that repulsion. So A would be the easiest, and C must be the one in the middle. So if you were to take an atom in its gas phase and provide it energy, you could have those electrons that are in different energy levels move faster and faster. If those electrons move faster and faster and faster, eventually one's going to pop out. This is known as ionizing, and if it's the first one you do, it's known as the first ionization energy. So when we put energy into this species, an electron comes out. Now, since we have to put energy into this reaction, this is an endothermic process. So a neutral atom must have less energy to start with than its ionized form. So if we were to draw the energy of a neutral atom and then how that energy changes when we have the ionized form, we would put energy into the neutral atom. So let's say that was 0. That energy has to go somewhere, so this species must have picked up that energy. So why did I graph it as a negative value? Well, what is negative energy? Is there such a thing? Can you have not energy? Can you have a deficit of energy? No. The negative here is a direction. Energy when going into a reaction is seen as positive. That's endothermic. Endo, like endo and in kind of match. Energy that is a product or energy contained within products is given a negative value. So by saying this has a negative 1300 kilojoules, I'm not saying it owes 1300, I'm simply saying directionally it's going away from me. It's a negative value. If energy is in the products, or if we ever have a reaction where we produce energy, that's known as an exothermic reaction. Energy exits. And while that's not necessary, that's not relevant to this because this reaction doesn't produce energy, it requires energy. It's just good information to know. The first ionization energy for hydrogen is 1300 kilojoules. And yes, it's a product, so it would be a negative 1300. But for simplicity's sake, 1300 kilojoules, you pump 1300 kilojoules into a neutral atom of hydrogen, and you get a hydrogen ion. If you do the same thing with helium, no electron's going to pop out until you've provided 2300 kilojoules. So why is that? What is different about hydrogen than helium? And I know you're smart, you're pretty, gosh darn it, people like you probably can find the difference. It's the E. No, I'm joking. It's the number of protons. Remember back to our examples where we had 1 proton versus 2 protons, and we said, oh, well, this has more charge in the nucleus, so this would require more energy. Now we can give this actually a name. This would be an example of what looks like for helium's electrons, and this would be an example of what it looks like for hydrogen. So it kind of makes sense. This attraction is weaker than this one. And so while this only required 1300 kilojoules, helium required 2300 kilojoules. Now the amount of energy that takes gives us an idea like this electron is probably a little further out than this electron. But we will talk about that some more in a bit. So when we think of lithium, well, lithium, you would say, Professor, lithium has 3 protons, so it's going to require even more energy. So like we had a difference of 1,000, so maybe you'd be like, oh, this is going to need 3,300 kilojoules. However, if you take an atom of lithium, put it in its gas phase, and pump it full of energy, you'll get an electron not at 3,300, but 520 kilojoules. A massive drop. Because, all right, we went up 1 proton. That caused us to need more energy because there's a greater charge in the nucleus. But when we got to lithium, a greater charge of the nucleus didn't count. We went down. It was easier to remove an electron from lithium than it was from hydrogen or helium. What could be doing that? Again, if we think back to our examples, we've talked about, hey, this was hydrogen, that was hydrogen, helium would probably look something like this, and we said, okay, that kind of makes sense. But now we're at lithium. Lithium has 3 protons, but it's got 3 electrons. Now, around that nucleus, there's only so much space. So if it has to fit 3 electrons, it must be kind of like if you go to a dance and you've got 1 dance partner, you could have a second dance partner dancing on your left as you do on your right. But if someone else wants to dance with you, they have to like come out to the side, and now you're like in the middle of a mosh pit of 3 people. That electron on the outside is much further away because these electrons around the nucleus form a shell, and they shield the nucleus from outside electrons. So again, when we say we want to ionize something, that means we're going to remove an electron. So when I pump this atom of lithium with energy, that inner shell, those core electrons, the ones near the nucleus, shield the nucleus, and the electrons in the outside, the valence electrons, absorb that energy, move faster and faster until they are bounced out. So that's why lithium requires less energy than the other two examples. So it's kind of like dancers on a floor again. Around the nucleus, you can have a dancer on the left, a dancer on the right. We must have this other row of dancers where an electron is. So how many electrons, how many more dancers could fit in this outer mosh pit around the nucleus? Well, if we take this experiment and do it with atoms from the entire second row, we'll skip a couple just for simplicity's sake, we see that sure enough, as we add protons, it gets harder and harder to remove an electron. The more protons you have, the more energy it took to remove an electron. Up to a certain point though, because remember that wasn't true for those first couple elements. For hydrogen it was 1300, and for helium it was 2300, but then we made a new shell. So this gives us an idea that atoms have shells or energy levels that can hold different amounts of electrons. The first energy level could hold 2 electrons, and because they're both negative, they'll spread out. The second energy level, well, we don't know how many we could hold. Let's see what happens when we get one more proton, one more electron, and we end up making sodium. Sodium with 11 protons, a neutral atom would have 11 electrons. What would happen? Well, that amount of energy resets. We went from 20,000. So again, hydrogen required 1300, helium required 2300. Then we made a new shell and it built up again as we got more and more protons in the nucleus, building that next shell, that next energy level up to a certain point, and then there's no more space, so we have to make another shell, another energy level, which is what sodium shows us here. Sodium must be the start of a new energy level because there's just not enough space for all these dancers, all these electrons around that nucleus. The mosh pit is full. So we need a new energy level for that very next electron, the 11th electron. So based on what we've seen so far, that as you go across, it takes more and more energy to remove an electron because you get more and more protons in the nucleus. When you get to the next row on the periodic table, you build the next shell. So we could do some reasoning. For magnesium, we could predict a value for magnesium. Magnesium's first ionization energy has to be more than sodium, but less than beryllium. So beryllium's like 900, so we need something between 500 and 900, right? 500 for sodium, 900 for beryllium. So let's cut the difference. Let's say 700, right? And again, for silicone, it's got to be something more than magnesium because it has more protons in the nucleus. It's got to be less than carbon because carbon's electrons are nearer the nucleus. So you might say something along the lines of like 950. And again, we could keep going. Phosphorus would have to be more than 950, but less than 1300, and so on and so forth. And if we filled those in, if we took those atoms, put them in their gas phase, and provided them buckets of energy, electrons would pop out at these values. And so for that first one, like, yeah, we were really close, but like, yeah, we got a little off, and it's because, science is messy. But the statement holds true. As you get more protons in the nucleus, it becomes more and more difficult to remove an electron up to a certain point. Up to a certain point, you run out of space in that energy level and have to start building new shells. So if you take a single atom and took all of its electrons away, you could see how many electrons fit in any particular shell. So if we did this with argon, here are all the electrons of argon and how much energy it took to remove them. And right off the back, when you graph this, you start seeing that there's groups of them. It seems that about 8 electrons were very easy to remove. 2 electrons required a ton of energy, and this group is somewhere in between. So the first 8 came out no problem. The next 8 was a little bit more of a problem, and the last 2, it was a chore to get them out. On average, it took 400 kilojoules to take out those last 2 electrons. On average, it took 7,000 kilojoules to take out the first set. The middle set, we said, oh yeah, they're kind of close, but I think that's just an issue of scaling, right? Because if you average these numbers together, this averages like 60,000, give or take, which is pretty drastically different than that first group. So we have 3 distinct energy levels that these electrons fit into. The ones nearest the nucleus, the ones that required the most energy to remove, we would say is the first energy level. From the nucleus, it's the first one you come to. So electrons in the first energy level have the least amount of energy to start with, so they require the most energy to remove. Electrons that can't fit there have to start filling the second energy level. That's the second one from the nucleus. They have more energy than the first energy level, and therefore require a little less energy to remove. Electrons in the outermost shell, often referred to as the valence electrons, because they are in the valence shell, have the most energy to start with. And so it does not take a lot of energy to get one of them to leave. Valence electrons are going to be used a lot in bonding, so when we get to the bonding unit, it's going to be imperative that you be able to identify the valence electrons of an atom, the ones on the outside. And if you want to know how many electrons and how many shells an atom has, the periodic table is here to help you. Hydrogen and helium. Helium had 2 electrons in it, but when we got to a 3rd electron, we started a new shell. When we got to sodium, we started a new shell. The rows on the periodic table can tell you how many shells or what energy level the valence electrons are in. The outermost shell electrons will be in. So if you number your periodic table's periods from 1 to 7, it'll tell you how many shells there are. So if you picked any element on the periodic table, like let's say you wanted to know how many shells does radon have? Well, around radon, you would need 6 shells. I know this because radon is in the 6th period of the periodic table. That's why the periodic table has this weird shape to it. The first 2 elements, hydrogen and helium, only have 1 shell, so they're in the first row. Then lithium all the way up to neon have electrons that fill up to the 2nd shell, the 2nd energy level. And when you get to sodium, you start building your 3rd principal energy level. That's the fancy word for this, for what row it's in, principal energy level. So sodium all the way up to argon has 3 shells. This is where the periodic table's shape starts coming into play to help remind you of how many energy levels any particular element has. And we'll get into some more interesting situations like why are these numbers different? That's a story for later. We paused and continued working on our copper chloride lab. If you were in class, you did. If you weren't in class, then hopefully your lab partner collected the data for you. Remember, from the other day when it's in blue, that was data that you needed to record. So if you have your lab partner's number, please make sure you get the mass of your Dixie cup and calculate the mass of the copper within the Dixie cup. We also then watched this video talking about the shape of atoms. Now we know that electrons form energy levels around the nucleus. It's time to say, do all the electrons in the same energy level require the same amount of energy, and how would we know which ones came from where? To do this, we look at photoelectron spectroscopy data, or PES for short. PES data means we take a laser and shine it onto a particular sample. That laser provides a steady stream of energy, and then an electron comes out, and using magnets we are able to capture the amount of energy added in order to remove that one electron. Now when that electron comes out, it causes a little blip when the amount of energy has been added. So for example, hydrogen at 1.3 megajoules, so 1300 kilojoules, same as the first ionization energy, fun fact, hydrogen releases one electron. The size of the blip, or the x-axis here, is the number of electrons emitted. So that one blip is one. If we have helium, helium has 2 electrons. So the question that we're looking at is, how many electrons does it have? Okay, it's got 2. In that same shell, 2 electrons, if they required different amounts of energy, so since it was the same as first ionization energy, helium would be 2300, different amounts of energy would mean we would have 2 blips of approximately the same size as this one. If they required the same amount of energy though, the size of the blip should be different, approximately twice the size. So we take a laser, we shine it onto a sample of helium, and sure enough, we get a blip that's a single blip, but it's twice as big. So again, the size of the blip is the number of electrons. So this blip for hydrogen represents the amount of energy needed to remove the one electron from the first energy level of hydrogen. For helium, at 2300 kilojoules, you could remove either electron from helium because they're in the same energy level. So both electrons of helium requiring the same amount of energy means that this distance for helium is much smaller than the distance for hydrogen, because these electrons require more energy to remove. They must have a stronger attraction for that nucleus. Alrighty, how many electrons does lithium have? Again, you're smart, you're pretty, gosh darn it, people like you. You know that lithium would have 3 electrons, and we've talked about lithium. That was the example where we started seeing new shells. So we have 2 electrons in the first shell that are going to require lots of energy to remove, and 1 electron in the second energy level that's going to require very little energy to remove. And if you remember back, or if you want to rewind, that first electron is only going to require 0.5 megajoules or 500 kilojoules to remove. And then the next 2 are probably going to require a lot. So probably on the order of this first energy level for helium, so either about there or maybe even a little bit more because you have more protons in the nucleus, we should get something that looks like this. A spike representing 1 electron, very easy to remove, and 2 electrons very close to the nucleus, which required lots of energy to remove. And sure enough, booyah, that's what we've got. For lithium, with its 3 protons, it has 3 electrons. 1 electron in its valence shell, the one on the outside, and 2 electrons as part of the core electrons. Alrighty, let's talk about beryllium. Beryllium, we would expect to see 2 peaks. Beryllium has 4 protons, so it has 4 electrons. So the 2 peaks would be the first energy level and the second energy level. 2 electrons in the first energy level, 2 electrons in the second energy level, and when you do the experiment, again, booyah, 2 peaks, each with 2 electrons. So now, when we get to boron, boron has 5 electrons, and again, we'd have 2 electrons in the first energy level. In this second energy level, there are 3 electrons, so you would expect to say, okay, I'm going to see 2 peaks, one with 3 electrons and one with 2 electrons. The 3 electrons are going to require a little bit of energy, and the 2 electrons require lots of energy. And when we do the experiment, science throws you for a loop. Let's see what we've got here. 2 electrons requiring lots of energy. These must be the 2 electrons in the first energy level. The second energy level, we said, okay, we expect to see 3 electrons that require very little energy, so this would be our second energy level. But it looks like the second energy level is broken. It's split. We've got 2 electrons and 1 electron. So within the second energy level, there must be 2 sublevels. One that can fit 2 electrons and one that starts making again. Meaning the second energy level must like split in half? Well, what if we kept going? Like, what if we said, okay, instead of boron, let's go all the way across. Let's look at a couple elements in the second energy level and see what happens here. So we did boron. In that second energy level, we see a 2 and a 1. And then moving into carbon, a 2 and a 2. A 2 and a 3. So this is 4. This must be a spike of 5. This must be a spike of 6. But then after neon, you'd start making another shell. But look, see how these are pretty close to one another? That means that they must be in the same shell. So all 8 of these electrons for neon are in the second energy level, but we have 2 subshells here. A subshell of 2 and a subshell that can only hold 6. If you look at your periodic table, I told you the periodic table shape is to help you remember how an atom's electrons set up. So those elements in the first energy level are in the first row. Elements with 2 energy levels are in the second row and third row and so forth. But I never addressed this big gap in the center. But look at what we see here, this big gap in the center. We get 2 elements and then 6 elements. The reason that they are separated from one another, even though they have electrons in the same principal energy level, in the same shell, that shell is divided into a section that has 2 electrons and a section that has 6 electrons. Now, obviously holding 6 electrons is going to be a little more complicated, so these subshells have different designations. If you can only hold 2 electrons, a subshell with only 2 electrons is said to be an S subshell. This is not 1000% true, but you could think of it as 2 electrons. You can fit one moving upwards and one moving downwards, or one spinning downwards, because when they spin, they would spin in opposite directions. So within that shape, we could fit 2 electrons. So the shape of the energy level with 2 electrons in it is known as an S shape because it's a spherical shape. If you can hold 6 electrons, and again, you would break them up into ones that spin up and ones that spin down, 6 electrons means we would have 3 distinct shapes. These are known as p orbitals. The p subshell can hold 6 electrons. So one spinning in front of and one spinning behind the nucleus, above and below, to the left and right, 6 electrons would fit in 3 shapes. If you need to hold more than 6, you start getting some really weird shapes, and my analogy of in front of or behind really starts to break down. A subshell that can hold 10 electrons is known as a D subshell, and a subshell that can hold 14 electrons is known as an F subshell. So on the periodic table is actually broken into blocks to remind us of these subshells. The first two columns of the periodic table, including helium, would have electrons that fit in the first and second place around the nucleus. They would fit in an s orbital. So the first two columns of the periodic table have 1 or 2 valence electrons. Elements on the right side of the periodic table, so the 6 columns from boron down to titanium and from neon down to radon, form the p block, and they would have up to 8 valence electrons, but those 6 would be in a p subshell. Some periodic tables have different designations for how they number the families on the periodic table. Most of the periodic tables that I will have in this class for you number across the top 1, 2, skip a bunch, 3, 4, 5, 6, 7, 8. Sometimes you'll see them listed as 1A, 2A, A, and then down here these are like 3B through whatever. Or they'll list these as 13, 14, 15. A good trick is the last number, the number in the ones column on the column, can tell you how many valence electrons there are for the representative elements, those in the S and P block. This is a generality, so it's not 100% true all the time, but it is a good place to start since this is only your 3rd day in chemistry. If we were to look at these PEZ diagrams, we could actually number and name the shape, the energy level, and how many electrons there are. This is known as an electron configuration. So this spike here is the first energy level, and it has 2 electrons in it. So if you can only hold 2 electrons, you're an S sublevel, so this spike denotes electrons that are in the first energy level in an S orbital with 2 electrons filling that orbital. The electrons out here are both part of the second energy level. We've got a spike of 2 and a spike of 6. So this spike is our second energy level. We can only hold 2 electrons, so it's an s orbital, and there are 2 electrons filling that orbital. The spike here is our second energy level, but it can hold up to 6, so we call that a p orbital. These designations can be drawn from the periodic table without actually running the experiment in what's known as an electron configuration, saying where the electrons are located relative to the nucleus, what shape they occupy, and how many electrons are within that particular sublevel. So this is known as electron configuration. So for neon, it would be 1s2, 2s2, 2p6. If we wanted to do this with oxygen, looking at the PEZ data, oxygen has 2 electrons very near the nucleus. So that's our first energy level with 2 electrons. It has to be an S. So 1s2, oxygen would start 1s2. Within oxygen's second energy level, we have 2 sublevels. So in the second energy level with 2 electrons in it, this must represent our 2s2, and this must represent something that can hold up to 6 electrons, but it only has 4 in it. So 2p only has 4 electrons in it. And that's how they would be different, that highest energy level is different. Ultimately, it is just the highest principal energy levels, S and P orbitals, that make up your valence electrons. So neon, a noble gas in column 18, has 8 valence electrons. The highest S and P orbitals for oxygen would be 2 plus 4. Oxygen in column 16 has 6 valence electrons. Those electrons will be the easiest to work with, so they'll be used in bonding, or we will remove them or add to them. You actually don't need the PES data in order to write an electron configuration. If you remember that the first two columns are S, these are P, you can write electron configuration simply by reading across the periodic table. When you get to the end of a line on a piece of paper, you go to the next line. It's the same on the periodic table. Read from left to right. When you get to the end, go down to the next row. Within electron configuration, you always say what principal energy level you are in when you change the sublevel. So let's try this. For chlorine, if I was to write chlorine's electron configuration, or the ground state electron configuration, I'm just going to read my periodic table. Chlorine is right here. So for chlorine, the first electrons are going to go in the first energy level. They're going to fill an s orbital, and the s orbital can only hold 2. I could remember that just off the periodic table by saying, okay, I got to start. When you start reading, you start at the top of the page. So I'm in the first row of the periodic table. It's an S block. In order to reach the end of the page, I have to pass 2 elements, so that there's 2 electrons in that first energy level. Once you reach the end of a line on a page, you go to the next line. So now I'm in the second row of the periodic table because the electrons of chlorine would fill the second energy level. The first ones that come in will go into an s orbital. 2 electrons would be needed to fill that space, would be needed to fill that orbital. I've reached the end, but I'm going to keep reading across because it's like reading on a page. You read all the way to the end. I'm now in the P block, but there are lots of P blocks. So you have to say again that you are still in the second energy level because electrons will fill the s orbital of the second energy level. They now need to fill the p orbital of the second energy level. And there are 6 elements there to remind you that the p orbital fills when you add 6 electrons. This brings us to the end of the line, so we now go down to the next line on our page. Again, chlorine is right here. So we're now in the third energy level. Electrons in chlorine will fill the third energy level. The first 2 will go into an s orbital, when we will now start making a p orbital. And we would fill 1, 2, 3, 4, 5 electrons. You count the element you're going to. So you could do this with any element. There is something to note here. The d and f orbitals have different principal energy levels. That coefficient is bigger, is different for a reason. So let's talk about that. If we look at PES data for potassium, it would look like this. All I did was take the PES data that we had been looking at, which had been had been up and down, and instead I've turned it on its side. If we look at the values on the x-axis, this is a lot, this is a little. So these electrons here require the most energy to remove. They are my 1s electrons. There are 2 of them, so this is my 1s2 blip. These electrons are very near one another, so they must together make up a new shell that requires a little bit less energy to remove, so they're my second energy level. So this must be 2s2, 2 electrons filling it. This must be 2p6. These spikes are relatively near one another. 3 and 2 are way closer together than 3 and 29. So they must make my third energy level, where this would be 3s with 2 electrons and 3p with 6 electrons. The electrons that require the least amount of energy to remove must be my valence electrons in the outermost shell. So that would be my 4th shell. They would fill the s orbital, so this is 4s1. Electron configurations simply come from PES data. You can either just write them off the periodic table, or you could analyze PES data and determine what an element was. If I tell you this was potassium, but you see only one electron in the 4th energy level, that's an element with the same number of electrons as potassium. It would have similar properties to a potassium. So you wouldn't say it's a potassium atom, you would say it's similar to potassium. Now, if I simply add another electron, the PES data is going to change accordingly. So going up 1 from potassium, now calcium. Calcium would simply look like this, 4s2. Notice that really the only thing that's different, yes, the values are slightly different, is that this spike has a little bit less energy, so it requires a little bit more energy to remove, 4s, but now there are 2 electrons in it. Based off of what we've done, if this was 3s and this is 3p, where do you think the next spike is going to occur when I go to scandium, when I get a d orbital? Because it's not a p, scandium's that first one in the dip in the center. Those are known as the d orbital. D doesn't stand for dip, it's just coincident. It's just a trick of the English language. Either way, you most likely, like me, would say, oh, okay, well, it's in the same row, so it would probably be near this value. You'd probably get a spike like here, right? So there would be my 4d with 1 electron in it. However, when you look at the PES data for scandium, that spike isn't easier to remove, it's harder to remove. The d orbitals are actually inside of that energy level. In fact, if we kept going from scandium all the way to zinc, this spike will start migrating. This will not. This will stay relatively the same. It might go to 0.7 or 0.8, but it's not going to move very much. But every time we add another proton or electron, this spike is going to migrate more and more and more until when you get to zinc, they almost overlap. This spike of 10 electrons when you get to zinc is almost all the way down here. I think it's at like 3.1, while this is like barely moved past 8, 0.8. That's because the d orbital penetrates closer to the nucleus. D orbitals are actually part of the previous energy level. Now, that's a lot of jargon and a lot of vocabulary for you, so here's the easiest way to remember it. The d orbitals penetrate closer to the nucleus and therefore are always 1 energy level less. So when we get to a d orbital, we're not going to continue on. So when we get to a d orbital, we're not going to continue on. This is 4s. The next one, scandium, is going to start 3d. But when we leave the d orbital, the p orbitals are still following that same pattern we had done before. So they go back to 4p. We won't do very many examples of this, but if we get to the f orbitals, if you have any elements past where the f block takes place, where the actinide and lanthanide series occur right here, they actually penetrate 2 closer to the nucleus. So they would start not at 6 or 5, but the f orbitals start at 4. So personally, when I get my periodic table, and when you're taking the AP exam, your periodic table will not have any numbers on it. I always number my periods, and then I number my families. But when I number my periods, I always subtract 1, and so I would write this is 3, 4, 5, 6, and then the F block is 4 and 5. So when I get my periodic table for AP exams, this is what I end up with. I have something that looks like this, where I have handwritten in these values to remind myself that the d orbital is 1 energy level less than the row it's in. So if we wanted to do the example in your packet of iodine and write iodine's electron configuration, Iodine is all the way down here. This is gonna take a minute. So rather than talking jargon, I'm just gonna read it off the periodic table. Should go pretty quick. To get down to iodine, we start at the top of the page. So we're in the first energy level in s orbital with 2 electrons, brings us to an atom like helium. Anything else is going to have to fill the second energy level. An s orbital with 2 electrons would bring us to an atom like beryllium. More electrons means we are now in the p orbital of the second energy level with 6 electrons, brings us to an atom like neon. The third energy level will start being formed. An s orbital with 2 electrons would bring us to an atom like magnesium. Our third energy level will be complete when we get to 6 electrons in a p orbital, an atom like argon. From here, we can now go down to the 4th energy level being full. The first 2 electrons will fill an s orbital, giving us an atom like calcium. And then we reach the d block. Our d orbitals penetrate closer to the nucleus, so this is not 4d but 3d, and it takes 10 electrons to fill that orbital, giving us an atom like zinc. Once we get past zinc, we return to the 4th energy level, which will be a p orbital. 6 electrons will fill it, giving us an atom like bromine. From bromine, we now can start filling the 5th energy level. The first 2 electrons will fill an s block, giving us an atom like strontium. However, once we get to yttrium, that's not part of the 5th energy level, it's part of the 4th energy level. And again, it will take 10 electrons to give us an atom similar to cadmium. After we've filled our 4d orbital, we will return to our 5th energy level, which is now a p orbital, and we have 5 electrons, giving us an atom like iodine. Now, as you can see, that is a lot to write. So there is a shortcut. The shortcut is to write all the core electrons as the noble gas that they represent. Noble gases have a full s and p orbital, and this causes them to be very inert. They are at the lowest energy configuration they can be at. So noble gases, or when an s and p orbital is full, we can abbreviate that by putting the brackets and then what that noble gas is. In our iodine example, the last time we had a full s and p orbital was 4s2 and 4p6. So when we had this noble gas here, which was krypton. So I could have skipped all of that and said, okay, start at an atom of krypton and then begin building a valence shell of 5s2, 4d10, 5p5. And you would have an atom with a similar electron configuration to iodine. Noble gas configuration is a shorthand. You'll often see it in multiple choice questions. You are most likely not going to be asked to write the electron configuration on a free response. They will want you to write all of it to see if you remember that the d and f orbitals penetrate closer to the nucleus. So if they ask for the ground state electron configuration, they are asking for this. Ground state electron configuration means start at 1 and go till you're done. If they ask for the noble gas configuration, I will be amazed, but they're looking for you to start at the nearest noble gas without going over, and then build the valence shell. The AP exam has also occasionally asked for the highest energy level. Highest energy level will be simply the last one you wrote in the highest principal energy level. If you read the periodic table from left to right and write it as you read it, you will obey what's known as the off-bow principle, that electrons fill the lowest energy level possible before filling those above them. The off-bow principle is the reason that we filled 4s before we filled 3d. Now, everything in the universe is lazy, whether it's students or electrons or planets, everything goes to the lowest energy state possible. If I asked you, would you rather learn about ions and electron configuration today, or finger paint, you'd be like, Professor, I'm going to make a turkey and I'm going to finger paint it, because that is way easier. Everything wants to do whatever is easiest. So when it comes to having the least amount of energy, elements with a full s and p orbital, the noble gases, they have the least amount of energy. Their electrons are in this magical configuration where they don't need anything else. And so atoms will gain or lose electrons to be like a noble gas. So if the goal is to have a full s and p orbital, atoms will either gain or lose electrons to be like neon. So fluorine, for example, is extremely reactive. If you see a cloud of fluorine gas, it would be a brownish cloud that no matter what it touched, concrete, floor, water, anything it touches, it will immediately light on fire. It will oxidize. It will start ripping electrons off of things because it is one electron away from being that chill state that neon's at. So fluorine will pick up one electron. It will rip an electron off of anything, making a fluoride ion. We symbolize that it has picked up an electron by saying it has a negative charge. When you gain electrons, you become more negative. These are known as anions. Anions are negative. Generally speaking, nonmetals such as fluorine gain electrons and become more negative. They make anions. Metals, on the other hand, have too many electrons. Sodium has one more electron, has this extra orbital that if it could just get rid of, it would be like a noble gas. It would be way more chill. And this is why sodium, if you put it in water, immediately explodes. It has this electron. It's got a lot of extra energy. But if it loses that, it can be like, all right, I'm chill, man. I'm kind of cool. So what sodium will do is sodium will give that electron up, making a sodium cation. Cations are positive, right? Like cats have paws. Isn't that cute? Cations, cats, are positive. Anions are negative. Or you can remember that cation has a T in it, which looks like a plus symbol. So cations are positive. Now, when cations form, they leave an empty space. So for sodium, we could have left 3s and just said there's nothing there. It's kind of optional, but this empty space, the nucleus of sodium can support electrons there. It's just not utilizing it. So if you provide a cation, a metal ion with energy, that electron can become excited and jump from a lower energy level to a higher energy level. So you could take one of the electrons from sodium's 2p6, making it 2p5, 3s1. This electron has jumped up. It is excited. It's in an excited state. But what goes up has to come down. And when it comes down, it releases radiation in the form of light. And this is how fireworks work. We take metal ions and excite one of the electrons, and when it comes back down, within that fraction of a nanosecond, it releases that energy that it had in the form of light. And so every firework you've ever seen is simply metal ions being heated or excited into an excited state. So with that, we did page 21 in our packets, practice 11.1, just the electron configuration part. For number 2, it's asking you to figure out what the element is. If the element does not exist, if you come across one that's like, I don't know, 1p6, there is no 1p orbital. So that's a non-existent element. Just write, this element does not exist, or Na. Or does not exist. Pause the video and do page 21 if you were absent. Orbital diagrams are a way of representing electron configuration that denotes the spin of electrons. Electrons that spin up from physics, we've learned, will spin counterclockwise, or they'll spin to the left. But electrons that spin down will spin to the right. This means that electrons can occupy similar waves. Within a wave, within one of those shapes, we can have electrons going up and one going down. They cannot both occupy the same space at the same time. That's known as Pauli's exclusion principle. Two electrons cannot both spin up within the same orbital. So orbital diagrams show this spin. Each sublevel has a different number of orbitals associated with it. S orbitals, the S orbital, remember, corresponded to a single shape, so we will represent it as a single box, or in all honesty, a single line. So anytime we have an S orbital, it'll represent a single line. P orbitals had 3 different shapes for the 6 electrons, 2 electrons for each shape, quote unquote. So P orbitals, anytime we have a P orbital, we will have 3 lines. Sometimes you'll denote them by the axis that the P orbital exists on. In this class, if I don't provide it for you, you can just write P and leave 3 blanks. Now, whether we use every single blank or if we use only one of them, you must draw all of them to denote that you know that the P orbital is only full once all 3 shapes are full of 6 electrons. The D orbital with 10 electrons means we have 5 different shapes, so 5 lines. And while it is extremely rare, at least at this level, if you need an F orbital with 14 electrons, you would use 7 shapes, so 7 lines. Now, when you fill your orbitals, we will not put 2 electrons spinning in the same direction in the same orbital, meaning you cannot put 2 ups immediately next to one another, you cannot put 2 downs next to one another. An orbital will fill when there's an up and a down. And orbitals fill like seats on a bus. If I open up this bus, it fills. I open up this bus, it fills. But when this bus opens and I have 3 seats, what psychopath, when they get on the bus, is going to be like, I'm going to sit with this person? No, if there are seats available on a bus, you spread out. That's known as Hund's rule. Electrons being negative will spread out within a sublevel. So if there are spaces within a sublevel, you will spread your electrons out. In other words, if you draw all your up arrows and then come back and do your downs within a sublevel, you'll obey Hund's rule. So the easiest way to do an orbital diagram is to start with the electron configuration. So why don't you pause the video, pull up a periodic table, and write the electron configurations for selenium and for oxygen. All right, welcome back. Selenium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4 would be selenium. So to fill selenium's orbital diagram, we're going to show the increasing energy as we fill these orbitals. So selenium 1s2 means in the first energy level, the s orbital, we will put 2 electrons. One will spin up, the other will spin down. 2s2, one spins up, one spins down. 2p6 means in the 2p orbital we will fit 6 electrons. If we do all 3 ups and then come back and do all 3 downs, we will obey all of our rules. 3s2 means we'll do 1 up, 1 down. 3p6, again doing all of our ups, then coming back and doing our downs will make it so we don't have any problems. 4s2, 2 electrons. 3d10 is the next one to fill. And if you look on this diagram, notice that 3d is a little bit more energy than 4s, but less than 4p, because the d orbital will fill before the p orbital. So we'll fill these 10 electrons, all of our ups, all of our downs, and now we can fill 4p4. 4 electrons means 3 up with just 1 down. For oxygen, I purposely gave you one you have to do by hand, and that's because on the AP exam, you will most likely have to write out an orbital diagram by hand. Simply doing lines where you denote what the lines are will be enough to earn you those points. So here's where I would start. I would take all my principal energy levels and sub-levels, and I would draw the lines to represent those orbitals. So 1s2, 2 electrons, 1 up, 1 down, 2s2, 1 up, 1 down, 2p4, go in and fill all of them with ups, and any left over are going to be down. So 3 up, 1 down. Orbital diagrams, again, are just an extension of the electron configuration, which was an extension of photoelectron spectroscopy data. And unfortunately, you do need to know all three. And if you ask, Professor, why do I need to know this crap? Well, it kind of helps to know how fireworks work. Or like you can impress your friends, be like, every time you see a green firework, that's either barium or copper. Anytime you see a red firework, it's most likely strontium. But if that's not enough, orbital diagrams also explain a quantum phenomenon known as magnetism. In class, we watch the video on what causes things to be magnetic, but they don't go over the definitions. So when it comes to things being magnetic, if something responds to a magnetic field, it is known as paramagnetic. And things that are paramagnetic have at least a few unfilled shells. So elements near the middle of any block will be paramagnetic. They'll respond to a magnetic field. Even simple or small elements like, for example, oxygen. You can use a very strong magnetic field to attract pure oxygen. It's not great, but there is videos where you can watch people fill balloons with oxygen and then attract them with a magnetic field. It's kind of cool. But elements that begin or end any block are known as diamagnetic. They respond to no magnetic fields. This is why zinc is a diamagnetic. You cannot get zinc to respond to a magnetic field at all. That's why like a lot of your change in your purse is not really magnetic, because most of them have a zinc core. Now what's around that core can be attracted to a magnetic field, so get me a strong enough magnet and you might have pennies that are coated in copper, which is sometimes referred to as ferromagnetic. Elements in the exact middle of blocks, specifically the D and F block, are extremely magnetic. So for example, iron is the namesake of things that are ferromagnetic. You used to have to know this for the AP exam. You don't necessarily, at least not in 2021 when I'm recording this video, but it is good information to know. Diamagnetic, magnetism dies, are the beginning or end of any block. Paramagnetic is anything in the middle, and ferromagnetic is only a handful of elements in the exact middle of any of the D or F blocks. With that being said, we are now done with Unit 1.3. Make sure you finish your 1.3 questions in AP Classroom. Next class, we will talk about periodic trends, which is a very short lesson before we take our test.